So what I'd like you to do is just, it's going to be quite simple. You're just going to write the unknown cations found and the unknown anions found. You're going to get your unknown from the stock room. So this is after you finish your known. Your unknown is not likely to have all these. You know, it's going to be some number of them. So you're going to have different scenarios that happen. So for example, one scenario might happen that there's no silver and there's no lead. If there's no silver and no lead, what's going to happen with the HCl? When you add the HCl, nothing's going to happen because you need silver or lead to precipitate with the HCl. And so if your unknown consists of barium and manganese, then you get no precipitate here. And so you're adding this HCl and nothing's happening and not getting any precipitate, then you figure, well, I'm not going to go down this branch. And so I always get this question. The question is, well, nothing happened here. Should I filter it?
No.
Well, no, there's nothing to filter, so don't filter it because you're trying, when you do a filtration, you're trying to capture the precipitate, you know, but they're reading along the instructions. And so this is why it's much easier to go along the flow chart because then you can see I'm going to skip that entire branch here. So if nothing happened here, I'm just going to skip that and move on. Right? Or another scenario that might happen is, okay, I get a precipitate, but that precipitate dissolves in hot water. What does that tell you? That precipitate dissolves in hot water. It tells me that, well, it's not silver chloride, it must be lead. And so I don't want to filter that either because that filtration step is for silver chloride. But people will filter it anyway. They're going to filter out the lead, and when they add the sodium hydroxide, nothing happens. It doesn't turn black, and they go, what? It didn't turn black. Well, it's not going to turn black because it's not silver chloride you captured in the filter. Did you catch that? I mean, does that make sense? And so what this requires is this. You could cookbook the known because, you know, the procedure is written for the known. But you can't cookbook, that is, cookbook means just follow the instructions. You know? You can't do that for the unknown. You have to, you know, be able to see where you're at and jump around. And so if we did get a precipitate, great, you know, let's see what happens with that precipitate here. But if you did get a precipitate here and you tested positive for silver, there could be other cations in the unknown. So we're going to test for the other cations, you know, here. And so the same thing holds as we go down the list. You know, here you may or you may not get a precipitate. If you get a precipitate and it's yellow, that's going to be positive for lead. But if you didn't get a precipitate, then what do? You just move on. You know? Obviously, you want to make sure you added enough Ki to make sure that there's a precipitate. You want to make sure you added up enough HCl, but you know, after a point, you go, oh, nothing's happening. You know, even with additional drops, nothing's happening. And so we may or may not get a precipitate. If we don't get a precipitate, then where do you go? You skip this, and then you keep going down. The list here. And so the one other factor you have to worry about is, let's say, you know, we're adding a whole bunch of HCl, we're adding a whole bunch of Ki, we're adding a whole bunch of NaHSO4. You know, and if those aren't precipitating, then those remain unreacted, so the solution is becoming more and more dilute. And so you have to be aware of that. You know, as the solution volume grows, it becomes harder to detect the species. And so if the solution volume is getting too big, what you might think about doing is to boil off some of the water, which you can do too. But that's only in extreme cases. All right, again, this step you got to watch out for. You know, if we get this light brown precipitate, we're going to dissolve it in some nitric acid, and then add some of this solid. What is this? This is called sodium bismutate. What do you know about sodium bismutate? What do you know about sodium? Does anybody know something about sodium bismutate from last time? Yeah, well, most of the stuff is toxic, but this one is also quite dangerous because it's a powerful. I told you not to generate a dust cloud of this because your lungs might start to fill up with fluid. It's a powerful it's a powerful oxidizer. In fact, this stuff I'm going to put in the hood over there. It's sitting in the hood over there. Because in the past, I asked this question. I asked you, and nobody knows. Nobody really cares because they just want to cookbook this and get out of lab ASAP. But some people generate a huge dust cloud. It used to be outside. And one student generated a huge dust cloud of sodium bismutate. They didn't care because they didn't know anything what sodium bismutate is, even though I said, watch out for this stuff. It's quite dangerous. So you don't want to do that. It's like this. I was just reading this. Did you hear about that manager at Buffalo Wild Wings? Yeah, this 32-year-old manager at Buffalo Wild Wings. I guess somebody accidentally mixed like bleach with descaler, and it started generating green gas. And so with this green gas, they had to evacuate the restaurant because it was causing discomfort for the employees and the customers. Except the manager stayed behind to clean it up. Well, the manager stayed behind to clean it up and ended up dying from that. That just happened 2 days ago, I think. Yeah. And what was that gas? The gas was chlorine gas. Chlorine gas is a powerful oxidizer. It's going to cause some severe lung damage, right? And so this stuff is more powerful than chlorine, and chlorine's what killed the guy 2 days ago. Okay, so just be careful with this stuff. It's pretty easy to avoid contact. It's like, but you don't want to be careless with it. That's all. So I put it in the hood, so in case some dust is generated, it'll get sucked out the hood. Permanganate is a powerful oxidizer itself. And so permanganate is one of the most powerful oxidizers on our list that I pass out. I'll pass it out later. But we need an even more powerful oxidizer. So we're going from manganese 2 here, using a more powerful oxidizer than permanganate. So we're going from a stronger oxidizer, sodium bismutate, to a weaker oxidizer, permanganate. But permanganate's no weak oxidizer. Permanganate's a powerful oxidizer. Yeah. And so just watch out with the sodium bismutate. Don't be careless with that. What else do you want to watch out for in this lab? What else you want to watch out for is silver nitrate. Watch out for that stuff, because what does silver nitrate do? Turns your skin black, basically. And in high enough concentrations, it'll cause blisters. Yeah. And lead. We want to watch out for lead, heavy metal, poisoning, toxic. And sodium hydroxide, eye hazard. And HCl. HCl has corrosive fumes, so you got to watch out. And one other one that's quite dangerous. We keep it in that hood there, and it has a little plunger. What was that in that hood with the plunger bottle? No, sodium bisulfate, don't worry about that stuff at all. But this stuff you want to worry about. Concentrated can cause third-degree burns. Concentrated sulfuric acid. It's coming out of the auto dispenser. It's going to get hot. Don't get any on your skin. You want to dump it in the waste. It's sitting in the hood in the auto dispenser, we call it. You twist up the syringe. You guys remember? I know it's last week, but so probably forget a lot of stuff. But you kind of twist up the syringe and then twist it down so it dispenses nice and slow. And it's viscous. It's really thick, so it's going to sink to the bottom of the test tube. Don't hold the test tube with your fingers, because it's going to get very hot. So what we're going to do is, for part two of this report, this is what I want you to do. I want you to write all the reactions that are occurring in this lab. And so this is the way I'm going to set it up. So part two, you're going to want to do something like this. Ag plus HCl. Ag plus HCl, what's going to happen? You're going to get a precipitate of AgCl, solid, plus H plus. This is going to be a composite of ionic and conventional or complete equation. Pb2 plus HCl is going to give us what? PbCl2, solid, plus 2 H pluses. And then what we're going to do is we're also going to see what happens with barium. Ba2 plus HCl yields, what would it yield? It'd yield BaCl2, but BaCl2 is aqueous. So there's going to be NR here, no reaction, because there's no driving force. This is not a precipitate. It is not a gas, and it is not a weaker acid from a stronger acid. Okay, next we have manganese 2 plus HCl. Manganese 2 plus HCl is going to give us manganese 2 chloride. Well, manganese 2 chloride, will that precipitate? No. Plus dot dot dot, plus dot dot dot. And so in this case, we're going to get no reaction too. And so the HCl is only going to react with the silver and the lead. And then we heat it. The symbol for heat is delta. We'll heat this. The silver chloride, nothing happens with heat, and we're left with silver chloride solid. However, the PbCl2 dissolves, so we're going to end up with PbCl2AQ. And the H pluses will still be in there. All right. Okay, what do we do next? Well, what we're going to do next is this. We're going to add to the silver chloride, we're going to add sodium hydroxide. So 2NaOH. Okay, what this is going to do is it's going to form, actually, do it like this. We'll add NaOH. This is going to form silver hydroxide plus chloride. Silver hydroxide is solid, but silver hydroxide decomposes. And so what we end up with is this. We end up with 2 silver hydroxides that decompose into silver oxide, solid, plus H2O liquid. That's what we have. All right, now continue this down here. Some more room. So this is done with this branch. So that's the left branch there. So you're going to write this all on a piece of paper. So just write it in your notebook for now. Okay, the next thing we're going to do is we're going to go down the right branch there at the top. So when we go down the right branch, we know that PbCl2 aqueous is actually Pb2 plus plus 2Cl minus. And so what we're going to do in the next step is we're going to take Pb2 plus, Ba2 plus, and Mn2 plus, and then add Ki to this. Add Ki, add Ki. Well, lead ions like iodide ions, and so we'll need two of those. So we're going to get PbI2 solid plus 2 potassiums to balance. Ki is actually just potassium ions and iodide ions. Potassium ions and iodide ions. Okay, barium iodide doesn't precipitate. And so what we end up here with no reaction, and manganese iodide doesn't. Iodides are all soluble except for silver, lead, and mercury. And therefore there's no reaction for those. Okay, then we're going to move on here with just barium and manganese. So we're going to separate out the lead, and we're left with barium ions and manganese ions here. So what are we going to do with barium and manganese? We're going to add sodium bisulfate here, plus sodium bisulfate. Sodium bisulfate consists of sodium ions and bisulfate ions. Well, what's going to happen here with barium is barium likes sulfate, so it's going to knock the hydrogen off this. Knocks the hydrogen off, takes the sulfate. And it's going to leave sodium ions and hydrogen ions left. Barium sulfate, well, sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium. So barium's an exception, so that's going to precipitate. However, manganese sulfate is soluble, and so we end up with Nr here, no reaction. And so that takes us to this here. And so now all we're left with is manganese. And so let's take a look and see what happens with the manganese next. So we take that manganese. Manganese likes hydroxide. And so in this next step, we're just going to take manganese and then add sodium hydroxide to this. And we're going to precipitate out manganese 2 hydroxide, this, plus 2 sodium ions here. So we'll need 2 sodiums to balance it. Sodium hydroxide consists of sodium ions and hydroxide ions. So what I'm doing is a composite between ionic and net ionic. Conventional equations. All right, once we have this manganese 2 hydroxide, then what are we going to do with that? Well, what we're going to do with that is we're going to dissolve it with nitric acid first. And so we can start like this. Manganese 2 hydroxide plus HNO3. We need 2 of those. What this is going to do is it's going to form manganese 2 plus 2 waters to a liquid plus 2 nitrate ions. Yeah. Okay, in the next step, we're going to react it with this sodium bismutate. So in the next step, we're going to take our manganese 2 plus and react it with sodium bismutate here, just solid. Okay, and so what's that reaction? Well, we know the product of that reaction, and later on I'll show you how to derive these equations. But for right now, we're just going to do it like this. And so I'm going to modify this equation a little bit from what they have here. And so the reaction's like this. We're going to need some acid, but it's going to give 2 manganese 2 plus, rather than writing 14 hydroniums like they do at the top there, I'm just going to write 14 H plus, like this, plus 5 sodium bismutate solids, plus 5 sodium bismutate solids. There. This is going to form 2 permanganates. 2 permanganate. And 5 bismuth 3 plus. 5 bismuth 3 plus. And I'm going to get 14, 6, 7 H2O liquid. I have to, since I don't have it as hydronium, I've got to cut down some of the waters over here, keep it balanced, and 5 sodium ions. And so basically this, our manganese 2 plus is our reducing agent. The H plus in the sodium bismutate, this is our oxidizing agent, our OA. And so what we're doing is we're going from a stronger OA to a weaker OA. Now permanganate tends to be a pretty powerful OA in itself, but it's going to be weaker than sodium bismutate. And so sodium bismutate is going to need some acid to get this to work. And then the bismuth is going to change. You know, bismuth over here, well, oxygen is -2 times 3 is -6. Sodium is plus. So -6 plus gives us -5. Bismuth is +5 here. So we're going from bismuth 5 to bismuth 3. And so the bismutate is taking some electrons. Who's it taking the electrons from? It's taking from manganese, because we're going from manganese +2 to manganese 7 in permanganate. And so this is the driving force. This would be the reducing agent in the reverse. So we're going from stronger reducing agent, stronger oxidizing agent, to weaker oxidizing agent, weaker reducing agent. And so this is the final step. In this step, what we're going to do is, this is light pink. Manganese 2 plus is light pink solution. Light pink solution. So we're going to go from a light pink solution to a dark purple solution. The permanganate forms a dark purple solution. Or, you know, you're just looking for something that looks like grape juice. This looks like grape juice. Not with white grapes, but with colored grapes. Okay. Let's just read here, since I don't know how many people actually read this. How many people read this? In Chem 4, you find nobody reads. But, you know, that's a bad habit to get into, because, you know, as you advance, classes get much harder. You know, every semester, every quarter, the classes, I thought, wow, that was the hardest class I took. And then the next term, you have even harder classes, more demanding. So, but you know, it's not something to get discouraged about. It's something to you get used to it, basically, and it's just normal. But to make that transition easier, you know, it helps if you read this stuff. You know, because then the next class isn't as hard, and it's not as much of a shock to your system. But anyway, let's read this. There's a lot to read in this lab, and so but this is kind of important. The observation required to confirm manganese 2 is the formation of the red-purple color of aqueous permanganate. However, the color of the solution is usually obscured by a suspension of dark insoluble solids. These dark solids form when not enough sodium bismutate is added, or when some chloride impurity is present. This causes the formation of permanganate to stop, and dark brown manganese oxide, manganese 4 oxide, to form instead. If this happens, add more sodium bismutate and filter the mixture to see red-purple color permanganate. So you're just going to keep looking for red-purple liquid. It could be on the surface of the solid or somewhere. You know, and so even if we fill on a brown precipitate, we're going to keep trying, you know, to get it. A lot of people have difficulty with that test. Right? All right, so those are all the reactions for that. And then for the ammonium test, let's look at the reactions for that. And so the unknown report part's going to be easy. Just list it. The known report part is going to be easy. It's going to be easy because all you're going to do is you're going to, are you guys writing this down? All you're going to do is write this down on a sheet of paper, showing me all the reactions that are happening. It's easy, but for some it's going to be impossible because there are some people who don't read and who don't write anything as well. And although most of the reactions are in this, so you can find them, and so I tell them, all the reactions are written in this write-up. Just organize them for me. And so the other part is this, for the ammonium test. Okay, so we got ammonium, we got silver ions present, we got lead 2 ions present, we got barium ions present, we got manganese 2+ ions present. And in this step, what we're going to do is we're going to add sodium hydroxide. So this is the ammonium test. We add sodium hydroxide. What happens to the ammonium? Well, ammonium gets converted to ammonia and water. And then what we do is we let the ammonia evaporate out of the solution, or we warm it up. And so we end up with ammonia gas. Ammonia gas plus red litmus. Red litmus I wrote down as HILT. This is red litmus. Gets converted to blue litmus. And so red litmus is an acid, and ammonia is a base. So ammonia will pick up that extra hydrogen here, and we'll end up with LIT minus. This is blue litmus. There's actually a formula for this, but we're not writing it all out. It's an organic acid, so it's a bit, formula's a bit more involved. Anyway, that's what's happening to that particular reaction. But there are some side reactions that occur here. These are going to be side reactions. The side reactions can give you clues. So for example, if silver ions are present, then that's going to react with sodium hydroxide. What forms? Silver hydroxide. Is silver hydroxide stable? No. No. Eventually, 2 silver hydroxides will decompose into a silver oxide plus water. And so silver oxide is the black, PPT. Lead 2 hydroxide, what color is that? This is a white PPT. Barium hydroxide. Well, hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, and barium. So barium is actually not going to precipitate. So with barium, we get no reaction with sodium hydroxide. With manganese, we'll get a light brown precipitate of manganese 2 hydroxide. Light brown PPT. So these are some side reactions that can kind of tell you what else might be present in the ammonium test. Ammonium test is a standalone test. Then let's look at the reaction for the chloride test next. The chloride test is, we just add what? And so what are the potential anions that we have? We have chloride, we have sulfate, and we have nitrate. So what we're going to do is we're going to add silver nitrate to this. When we add silver nitrate to chloride, a solution containing chloride, we're going to precipitate out silver chloride solid. And we'll have nitrates. When we add it to sulfate, we expect to precipitate here, but silver sulfate is borderline soluble. And so we end up with no reaction here. Silver sulfate is on the border. So it might precipitate, might not precipitate, but at the concentrations we're using, it's not going to precipitate. And with nitrate, there's no reaction. And so the only thing that silver nitrate should react with is chloride. The others should be no reaction. Okay, the sulfate test, well, we have 3 possible anions. Now, the known solutions, you have a separate known for the cation and a separate known for the anion. The anion known solution is in the back there. The cation known solution you get from the stockroom here. When you go pick up your unknown is going to contain both the cations, unknown cations, and the unknown anions. And so you have to make sure you have enough unknown mixture to test. You know, for the main part of the flow chart, silver, lead, barium, manganese, and the ammonium test, and the chloride test, and the sulfate test, and the nitrate test. And so you got to make sure you have enough of those. Well, in the sulfate test, we're going to have chloride present, sulfate present, and nitrate present. And then what we're going to do is we're going to add barium, adding barium nitrate. We add barium nitrate here, we get no reaction. You know, barium chloride's soluble. It's not going to precipitate. There's no gas. There's no stronger acid to weaker acid. However, barium and sulfate like each other here. Barium and sulfate like each other. They're going to precipitate out barium sulfate. And with PPT, we're going to end up with the 2 nitrates here. And then, of course, nitrate with barium nitrate, nothing's going to happen here. So we get no reaction. And so when we add barium nitrate, the only anion should react with is sulfate. That's it. Okay, finally, the nitrate test. Nitrate doesn't precipitate out with anything, so we have to use a different test. The different test is going to be taking advantage of a redox reaction here. And so take a look at this first part, and then let's do this. We're going to go chloride with sulfate and nitrate. And then tell me what happens when we add FeSO4, if anything happens here. All right, so when we do this, we're looking, okay, does iron, what is that, iron 2 or iron 3? Does iron 2 like sulfate or does it like chloride? Or neither, really? Well, neither. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. And so this is not a precipitate. Will iron precipitate out with chloride? No. And so this is NR, no reaction here. How about here? Here, sulfate and sulfate, there's going to be NR here. Here, there appears to be NR, right? But there's one more property of nitrate. That one more property of nitrate is a strong oxidizer. Sulfate isn't that strong of an oxidizer, and chloride isn't at all an oxidizer. And so this one has one additional property of being a strong oxidizer. And so we have to watch out for oxidation reduction type reactions. Iron 2 is a reducer, or can be. It can go either way. And so what we're going to have is a redox reaction that's going to occur between nitrate and iron 2. And so let's take a look at that reaction here. Let's see. We're going to look at chemical reactions in more detail once we get to the acid base and the redox reactor. But basically, this is the reaction that's written here: 3Fe2+, so this is my reducing agent, plus nitrate. Well, nitrate, we needed some acid here, so it's going to be nitrate plus 4H pluses. This will be my oxidizing agent here, nitrate and 4H pluses. This is going to do this. We're going to convert it from 3 iron 2 pluses to 3 iron 3 pluses. So each iron 2 is going to lose 1 electron. And the nitrate, when we look at nitrogen here, nitrogen is in the +5 oxidation state. But it's going to be forming nitrogen monoxide, or nitric oxide here, plus 2 H2Os. In the nitric oxide here, we have nitrogen in the +2 oxidation state. And so nitrogen is going to go from +5 to +2. It's taking electrons. It's taking electrons from the iron 2. Well, NO is a gas. And NO is a CCG. It's a clear colorless gas. It's hard to detect it. And so how can we detect NO gas? Well, you know how we can detect NO gas is we have excess iron 2. You need to make sure you put in plenty of the green iron 2, because if we have excess iron 2, then iron 2, which is green solution, reacts with an NO gas to form this weird species, FeNO. It's going to be 2+. And so the NO is going to stick onto the iron. Just like oxygen. Oxygen sticks onto iron 2 in your blood, in hemoglobin. And just like carbon monoxide sticks onto iron 2 in your blood, except it sticks a little too well and ends up blocking out oxygen. And so NO can complex, this is called a complex. This turns out to be brown solution. So what we're looking for is a brown solution. Now, this has to be fairly acidic, so what we're going to use here is this is going to be from the concentrated sulfuric acid. Concentrated sulfuric acid is nasty stuff. We need that for the acid part here. Give it to us. Concentrated sulfuric acid is quite viscous, so this brown solution is going to come here. The concentrated sulfuric acid is like maple syrup. It's going to be stuck down here, and it's CCS. So this is concentrated sulfuric. We're going to have excess iron 2 up here. This is going to be light green solution. like that. So we have light green solution here, and this is not as dense. In this brown layer should form right at the interface here. We should see a brown solution forming right here between the syrupy concentrated sulfuric acid and the iron 2 sulfate with nitrate. All right, so those are all the reactions. So on the report sheet, 2 parts. 1, just a list of the cations you found, anions that you found. 2, write down all these reactions for the analysis. All right, any questions? All right, we're going to go ahead and get started here. I'm going to skip the quiz today to save time.